Poor lift at low speeds. We have just demonstrated that in the swept wing, the speed component of the wing responsible for lift is lower than the real airspeed flown by the whole aircraft. Thus, lift is correspondingly reduced. There is no doubt wing sweep removes some basic lift. Check in the figure that idea. Observe that for the same angle of attack, the unswept wing produces more lift than a corresponding swept wing. Another way of interpreting this figure is that for a given amount of lift, a swept back wing must be flown at a higher angle of attack than an unswept wing. Conversely, to produce the same relative lift, the swept back wing requires more angle of attack. This slow response to changes in angle of attack means that things like a quick flare during landing are less likely to be successful in the jet aircraft. This poor lift aerodynamic matter is also of high importance in the way in which drag and lift vary with speed. The following figure shows how the total drag varies, comparing both the turboprop and jet aircraft. This shows a reduction down to low speeds, and then watch an increase with further reduction in speed. There is a point identifiable as the minimum drag point, which is the mark to identify the backside of the curve. That is, in the low speed range on the backside, reducing the airspeed actually increases drag. Flight on the backside of the curve requires you to take care with airspeed, not allowing it to reduce. In this region, drag increases faster than lift, and the end result is that the airplane begins to sink. Sink tendency may be corrected by putting the nose down and allow the airplane to accelerate above the minimum drag point. It's a quite unconventional maneuver and can rarely be used because it always involves height loss. You can also add thrust to accelerate the airplane, and a lot of thrust is required to overcome the drag and accelerate the airplane to gain altitude. This is valid for both turboprop and jets, with the exception that the speed at which this effect begins is much higher in jets. Moreover, in turboprop aircraft, this speed is well identified by the steepness in the drag curve, but it is quite flat, extended on the jet's curves. I just want to show you that if you allow the airspeed to decrease below the minimum drag point, the aircraft will quietly slide to the backside of the curve, and the jet does not produce noticeable changes in flying quality. Don't get caught by the situation. If you suspect you are entering in the backside of the drag curve, make a firm decision and simply add power with determination. Embraer does not recommend any approach with speeds other than those published in the Airplane Flight Manual. Flying in the AFM speeds and keeping the flat maneuvering speed published in the Airplane Operations Manual will maintain you in the safe region of the curve. Actually, flying the Embraer jets according to the rules gets you into the safe side of the curve. These aircraft have excellent handling qualities at low speeds. Yet, when compared to a straight-wing turboprop, there are differences. Obviously, pilots are supposed to fly at low speed for controllability reasons in a one-engine inoperative condition. But even if control is not a factor, it is very important that the low-speed end of the envelope be avoided to prevent a no acceleration, no climb situation from happening. And if it happens, the pilot must be aware that reducing speed will not increase flight path angle. Let me show you an important characteristic of the flight in high speed. Mach tuck. Observe the pressure distribution along the chord of a typical airfoil shown here in a subsonic speed and during shockwave formation. As the figure shows, the lift forces during shockwave formation act at a point nearer the trailing edge in relation to the subsonic flow, where the lift is predominant near the leading edge. If airspeed is further increased, shock waves move closer to the trailing edge. As it does, lift results. The more intense the shock waves are, the heavier the pitch-down tendency is. This can result in the aircraft accelerating rapidly to excessive high speeds. It is a phenomenon referred to as Mach tuck. If an input to the elevator is applied to correct for the pitch-down tendency, the angle of attack is now increased. The shock waves are boosted, and the pitch-down tendency increases accordingly. It may happen in a generic aircraft that in transonic speeds, if the pilot pulls the yoke to counteract the pitch-down tendency, the increase in the angle of attack shifts the lift force in the wing so far aft to a point that the end result is inverted. The aircraft tends to pitch down further instead of recovering. The Embraer jet aircraft has been extensively flown to Mach 0.85, and no tendency like the Mach tuck has been observed. Recall the maximum operating speed is Mach 0.78. Embraer does not recommend any flight excursions beyond the aircraft operating envelope. Should an excursion out of the operating envelope develop for some reason, you ought to know that some pitch-down tendency might occur at speeds in the vicinity of Mach 0.85 and over. The mild tendency can be safely counteracted conventionally. That is, pulling the yoke will cause the aircraft to recover. As a general policy, recovery should be done first by changing thrust and drag, then by using elevator. All these recovery actions should be done as smoothly as possible, but not allowing the aircraft to accelerate to even higher speeds. Speed brakes may be used to increase drag. Embraer tested the use of speed brakes at speeds up to Mach 0.85, with the aircraft trimmed for Mach 0.78. An additional recommendation arises when using speed brakes at high speeds. Deploying speed brakes at high speeds induces a pitch-down tendency. The pilot force to counteract this tendency is 9 kilograms or less when Mach is 0.85. Higher counteracting forces may be required at higher Mach numbers. Therefore, using speed brakes will make you also pull back the elevator. The aircraft maneuvering envelope. We have shown how serious an excursion to extremely high speed can be. But we have also demonstrated that the Embraer regional jets have shown safe operating characteristics with inadvertent exceedance of the Mach envelope. Nevertheless, if you combine the fact that operators opt to fly at high speeds and high altitudes with the potential threat of gust upsets or inadvertent penetration in turbulence, you, as a prudent pilot, ought to be aware of how the aircraft maneuvering envelope works. This is a chart documented in the approved AFM, which shows the low-speed buffet induced by stall and the high-speed buffet induced by the shock waves. Also, you can get the normal load factor or bank angle to buffet at a given Mach number, or the altitude margin at a given Mach number and 1G. At a given altitude and weight, there is a low-speed and a high-speed buffet boundary. In the example shown, there is a certain range in which the airplane can operate. The low-speed buffet is supposed to occur at Mach 0.70. If the aircraft accelerates to Mach 0.80, high-speed buffet will set in. The higher the altitude, the smaller the speed range between high and low-speed buffet. The lower the altitude, the greater the speed range. And the higher the weight, the smaller the operating speed range. The load factor G has a similar effect. Increasing load factor, as in making a turn, restricts the operating range. Pilots should become familiar with the buffet boundaries and the combination of weight, altitude, and speed at which they operate in order to anticipate any inadvertent excursion out of the envelope. Imagine an exceedance of the envelope during a turn. It might be difficult to distinguish between the high Mach number buffet and the pre-stall buffet. The unwise pilot may not recognize he is flying in the low-speed side of the envelope and incorrectly add power to speed up the airplane. Such an error will actually not help and will make the situation worse. Some care is necessary to know the maneuver margins, and for good reasons. Take a look at the buffet onset envelope in your AFM. Get the low-speed and high-speed margins, and fly always in a speed coherent with those margins. The dihedral effect.